All right, let's look at the skeleton and compare a mammal with the fish. And there are a couple of points that I want to make. We're going to talk in a little bit of detail about the vertebrae, but let's begin just by looking at these two skeletons. So beginning with the fish, remember fish have essentially no head mobility. So they have just one kind of vertebra, so that's just these trunk vertebrae, and part of them are involved in the tail here and so on. Notice that here, most of these pelvic fins here are not associated with that skeleton at all. Notice that the pectoral fins are firmly attached to the skull. Remember when we were talking about the evolution of the ears, and the fact that the otic capsules are at the back of the skull, here you can see why that is, right? Because vibrations in the water are going to hit the side of the body and be transmitted up to the skull in this way. They're also going to hit these things right here and be transmitted up to the back of the skull as well. So there are sound transmission implications for this particular architecture. Now, when you look at this thing, look at this cross-section over here, and notice all of these different muscle bundles. And between all of these muscle bundles, you have this connective tissue. And that connective tissue can become ossified. And that's what you're seeing right here. So these are all ribs. Holy smokes, you've got ribs everywhere on a fish. If you've ever eaten carp, you'll know that there are just ribs every darn where on the body of this fish. There are ribs going out, going down. There are ribs going out to the sides. There are ribs going up. There are simply ribs everywhere. By the time you get to a mammal, that's a fundamentally different scenario. So here you see ribs, downward ribs, upward ribs, sidewards ribs everywhere. Here in the mammal, the only place where you have ribs are associated with the thoracic vertebra. If you were to look at reptiles, what you'll discover is that you've got cervical ribs and ribs down here as well. So one of the things that's happened in the evolution of the skeleton, going from fishes through amphibians to reptiles to mammals, is a restriction in the location of the ribs. So the ribs are now in mammals confined just to this thoracic region. Why is that? Well, there are a couple of things that are going on. One thing that's happening is that the function of the ribs is changing. So in an animal like a fish, they are protective to some degree, but they're certainly not involved in ventilation of lungs or anything of that sort. The same is true in reptiles and amphibians. Ribs are simply don't serve any purpose other than protection. Now they're expensive, right? A lot of calcium goes into those things. So some animals that have limited energy budgets are not going to be capable of expending much energy or minerals in the production of ribs, and they don't. But in mammals, those ribs play an important function, both in protecting the organs that are up in here, the lungs and the heart, right? But also in providing a surface where you can have this muscle called the diaphragm, and that diaphragm is going to be used in active ventilation of the lungs. That's not something that happens in a reptile. Reptiles, amphibians don't have diaphragms. When they ventilate their lungs, they are ventilating the lungs in a fundamentally different way. There's this interesting paper by a biologist now at University of Utah, and he wrote a paper on how reptiles ventilate their lungs. And his name is Carrier, and he describes something that is now referred to as Carrier's constraint. When a reptile is walking, when the right front leg comes back, it's compressing the right-hand lung. And that lung is then evacuated. When the left front appendage goes forward, it's putting negative pressure on the left-hand lung, and that lung is then filled. So it's the motion of the front appendages which is ventilating the lungs. Interestingly enough, if you look at monotremes, or rather, if you look at marsupials, especially if you look at the skeleton of the opossum, what you'll notice that there are these two bones sticking out from the pubis, and they're referred to as the epipubic bones. And people originally thought that those epipubic bones were designed to support the pouch. But of course, there are lots of monotremes that have pouches which aren't in any way associated with those epipubic bones. And it turns out that those epipubic bones are attached via muscle to the bottom part of the body here, to the diaphragm, so that when the animal is walking, those two muscles are contracting and are actually involved in ventilation of the lungs. All right, so let's now talk about the vertebrae, and I just want to spend a moment with this diagram and just show you that evolutionarily we begin with the notochord up here, and then below that we have these somites, or these myomeres, these body segments. Okay, and if we go down this direction for fishes, or down this direction for amniotes, okay, so for the terrestrial animals, what you'll notice is that when we develop these centra are forming across these segments. Okay, so here's one myotome, here's another myotome, and notice how these centra bridge the gap between those two myotomes. And then on top of that, we form this structure called the neural arch, which is going to protect the dorsal hollow nerve cord. Let's look at what the evolution of that centrum looks like, because there's this interesting thing that happens. So let's look at this crossopterygian fish here. And here we see this here's the neural arch, and it's sitting on top of these two segments, these two myomeres. And we have this region of ossification here, and this centrum is actually divided up into two parts. There's a part called the intercentrum, labeled with an I, and another part called the plurocentrum, labeled with the P. And what happens in the evolution of the amphibians is that the intercentrum becomes really large and the plurocentrum becomes really small. And by the time you get to modern amphibians, here's this centrum, there's the neural arch. The centrum is made up entirely of the intercentrum, so the anteriormost part here. The plurocentrum has been lost. But if you look at the labyrinthodonts, right, so this group that actually gives rise to the reptiles and the mammals, you notice that the intercentrum becomes really small, okay? The plurocentrum becomes really large, okay? So that if you're looking at lizards and snakes and birds and mammals, our centrum is comprised of the plurocentrum. In other words, amphibians, the centrum on the vertebrae is fundamentally different than it is in everybody else. All right, let's now think just for a moment. There are just a couple of more points that I want to make. One has to do with the evolution of limbs. There's a lot of controversy in the evolutionary literature about where limbs come from. I want to address that and just present you the two different ideas. And then I want to talk about regionalization in the vertebral column. So there are two basic ideas for where limbs come from. One idea is this fin-fold theory, and another one is this sort of ray theory. And that's illustrated here in this particular diagram. So in the fin-fold theory, what you have is you have this flap of skin, and in this flap of skin you have these bony elements down here along the side, and you have all of these projections sticking out like this, right? And then by the time you get to actinopterygian fishes, you get these sort of rays that look like that. And in other sorts of fish, you get something, in dipnoid fish, you get something like that. And then in the crossopterygians, this sort of structure is reorganized, and you end up with a system that looks something like this. So you have one element here, and then multiple elements here, right? And then you get all of the fingers or all of the toes organized something like that. The most important point is this: in all vertebrates, it doesn't make any difference which terrestrial vertebrate it is. They all have the same basic design. That is, you have one element here and two elements here. And then everything else is just added on top of that. Now, it turns out that all terrestrial vertebrates have one element right here. Okay, so that's either your humerus or your femur. And then you have two elements right below that. Where's my pointer? Two elements right below that. So radius and ulna, or tibia and fibula. And then you have these bones either in the wrist, right, or in the ankle. And then you have 5 digits, always 5. Why is that? That's because the Crossopterygian fishes that gave rise to us had 5. There was another group of fishes, which were also lobe-finned fishes, and also followed this model, but instead of having 5, had 8. So it's entirely possible, had this other group of fishes not gone extinct, that terrestrial vertebrates would now be strutting the globe with 5 fingers, or with 8 fingers and 8 toes rather than 5. The reason that you have 5 is not an adaptation to anything, it's evolutionary junk, right? All vertebrates, at least embryonically, all terrestrial vertebrates, at least embryonically, have 5 digits. All right, I want to now talk about regionalization of the vertebral column. And you're looking at this diagram and you say, gee, John, you lied. You said that they all have one element up here and then 2 elements down here. And I'm not wrong, they do. One of the things that happens is that in both appendages, you oftentimes get fusion of elements or extreme reduction in elements. If you look at the tibia of ungulates, you will oftentimes see that the fibula is oftentimes just this little tiny shard of a bone, a little tiny spear, a little fragment of a bone, and or embryonically it becomes fused to the tibia. The same is true if you look at the forearm right here. In many animals, right, it's reduced or fused, but embryonically at least it's always 1 proximally, 2 distally, and then 5 down here. Okay, so let's think about now this skeleton here, and this is for a frog, and we had talked at some length when I was going around from group to group the other day. I was talking about sacral vertebra, and I made the point that in amphibians there is but one sacral vertebra, and you can see that here. Okay, and that's not a particularly powerful connection. What frogs have done, and remember, frogs jump, right? They hop, which means that they are imparting rather significant forces to that bone right there. What they do that is different from a salamander, which is not capable of jumping, is they cheat. So here's this frog, and it has that one sacral vertebra, which is a weak connection, but it's taking all these caudal vertebrae right here and fused them into a bone called the urostyle. And that urostyle is now butted up against the ischium back here. So what this animal has done is it's increased the strength of this girdle by 50% by adding this tripod-like connection at the back. So frogs are capable of jumping because they've cheated, okay? They've adapted. They've extended that bone and they've increased the solidity of the connection by 50%. The other thing that they've done, if you remember, what determines how high you can jump? Well, it's all force equals mass times acceleration, right? What have they done? They've reduced their mass. So notice they don't have a lot going on here in terms of ribs. And notice what's happening in the skull. There's extreme reduction of mass in the skull. So they've really cut down on the number of bones that are, not the number, but the extent of the bones that are in the head. Now, the other interesting thing when you look at a frog is that the number of vertebrae here is pretty reduced. And look at how extensive this girdle is right here. So you have the suprascapula, you have the scapula, you have the coracoids and all of that sort of stuff that's involved down here. This pectoral girdle is like a giant box. It's actually like a giant shock absorber, so that when the animal lands, it can absorb all the energy of landing. It's a big darn box. That's not what you have. You have this very sort of limited kind of connection there. And of course, the difference is that you have a range of motion in your pectoral girdle that far exceeds anything that this animal is capable of. Now, the other thing I mentioned when we were talking about the otic capsule and sound conduction routes, the other thing I mentioned was this, and that is that frogs have two auditory pathways. They are hearing ground-borne sound waves and airborne sound waves. They have two sensory papillae in the ear. One is through airborne sounds, and that's for high-frequency sounds, and the other one is across this girdle right here. So you have muscles, the opercularis muscles, which are going from here right back to the back of the skull. So that now all the sound vibration coming up through these arms, through this big massive girdle, are going to be conducted up to this point through that opercularis muscle and to the back of the skull. So they have two avenues of sound conduction, right? Not just one. We don't have that second avenue of sound conduction. All we're hearing is airborne sound waves. So notice this skeleton, right? It's a pretty robust skeleton, and that's the situation that you see in most vertebrates. Here is the other avenue for the evolution of limbs. We had talked about the fin fold theory. That's the idea that you have here, and going along that direction. Here is the other sort of idea where you're going from this sort of situation right here where you have these three elements. Those three elements become reorganized into this proximal unit and then two distal units, and then you end up with your 5 elements up there, your 5 digits up there. So those are the two basic ideas. It's an argument that was hot and heavy when I was your age. Either nobody cares anymore, or the recognition is that it'll be a while before we finally figure it out. I'm not sure which. All right, what I want to do now is just talk a little bit about the two girdles. I want to talk about the pectoral girdle, and I want to talk about the pelvic girdle. The pelvic girdle is pretty straightforward and simple. The pectoral girdle is a little bit more complicated. So we need to go all the way back to, not all the way back to ostracoderms, but to placoderms. Placoderms were these armored fishes. Remember, the ostracoderms had dermal armor, heavy dermal armor, and no jaws. Placoderms had jaws, but they had dermal armor, but the dermal armor was less extensive. And if we look at the placoderm condition, here you see all of the bones that are involved in the pectoral girdle. Okay, so you have a suprascapula, you have the scapula, you have the coracoids, you have the clavicle, the clithrium, the supraclavicle. I don't recall what that is. That's probably the pterygoids, and there's the skull. There's the glenoid fossa. That's where where what ultimately becomes the humerus is going to articulate. Notice what happens as we go from here, right, all the way up to early tetrapods, to primitive mammals, to advanced mammals, and all. What we're left with in advanced mammals is basically just the scapula, right, and the clavicle. So clavicle and scapula. We don't even have the suprascapula anymore. Although, if you look at the scapula, you'll discover that there are parts of the scapula, like the acromion and the metacromion, right? And then the coracoid, right? This little notch on one end. Those are the remnants of what all of this stuff was down here. So in mammals, the scapula has become really simplified. And the girdle is certainly much simpler than what you find in frogs or in reptiles. Okay, so the extent of that girdle is much reduced. Why is that? Well, what's important in mammals is simply that pectoral appendage in primates, for example, is involved in all sorts of activities. It's no longer all that involved in locomotion. If you look at wolves or caribou or any other quadrupedal vertebrate, the front legs are just there to steer. They're there to keep the chest off the dirt, right, and to steer the animal left, right, or something of that sort. That's really the full extent of what they're involved in. All the power in moving the animal forward comes from the pelvic girdle, not from the pectoral girdle. Everything that's happening in these modern mammals is all about either climbing or tool use or something of that sort, steering, keeping the chest off the ground. That's different from what you find in amphibians or in reptiles. If you look at the pelvic girdle, it's a much simpler sort of scenario. There are 3 bones in the pelvic girdle: the pubis, the ischium, and ilium. And it's the same in all of them. It's always those 3 bones. And the acetabulum is always in the same place. Okay? Sometimes the ischium is bigger, sometimes it's smaller. Sometimes the pubis is bigger, sometimes it's smaller. The proportions change, but it's always those 3 bones. So, in terms of evolutionary sort of showing evidence of adaptation, the pectoral girdle is by far more interesting and by far more complex and perhaps more difficult to understand. The pelvic girdle is pretty easy to understand because it's all about locomotion, about mechanical advantage, and it's pretty conservative. The pectoral girdle is not very conservative. It's pretty adventurous. There's a lot going on there. The pelvic girdle is not. It's conservative. It doesn't change much. Why not? Probably because the selective forces operating on it are so basic. It's all about moving the animal forward. There's not a lot you can do, right, to mess with it. There's not a lot you can do without messing that system up. So the system doesn't change all that much. I mean, clearly it's different in a mammal than it is in a reptile, right? But still, even within mammals, that pelvic girdle, what's going to change are the proportions, but not the basic layout. Those proportions, you can tell by looking at those proportions, just thinking about mechanical advantage and speed ratio. You can determine whether an animal is primarily a jumper or whatever, right, if it's not a jumper. But you can do those sorts of basic things by looking at the proportions. But otherwise, it's a pretty conservative structure. All right, that's it for today. I know that's a lot of material, but we're not in any rush with this. Presumably, we're going to have class on Wednesday. Don't know for sure yet. We'll see what they say. If we don't have lab on Wednesday, I will have some sort of material available for you online that you can work with. All right, see you.